Alright, class. Let's continue with gases. You had a take-home problem. Hopefully you did it. I know I still keep calling them take-home problems. Since you're home, I should come up with a better name. Alright, let's go and see how you did this. This problem, if you read the problem, it says we have one flask. Okay? We have one flask. And if you have one flask, what does that mean? If you have one flask, that means you have the same volume and you have the same temperature. Do you agree with me? Because if you're in the same flask, that means the volume is going to be the same and temperature is going to be the same because it's in the same flask. You have one flask. We have equal masses of N2 and O2. Okay, I'm going to cross that and I want to circle that. So far, so good. Now, the first question says, which gas has a greater pressure? So, the first thing I'm going to do, I'm going to write down PV and RT, right? PV and RT because that's the equation we know and we love. Now, after I write PV and RT, then I'm going to say that they are in the same, this one flask, they're in the same flask. And we said, if you're in the same flask, that means you have the same temperature and you have the same volume. So I'm going to cross out. I'm going to cross out volume and I'm going to cross out temperature. Because I said you're in the same flask. There's only one flask. Same volume, same temperature. Then I'm going to cross out R. Yeah, R is a constant. So now, what does that mean? That means if I'm looking for a gas with a greater pressure, which one would have a greater pressure? The one that has a higher number of moles. The one that has a higher number of moles will have a greater pressure because pressure and moles are on the opposite side. So they are proportional. If one goes up, the other one has to go up because they're on the opposite side. We're good so far? Okay. So we said they're on the opposite side. That means if I'm looking for the one with a greater pressure, I have to look at the one with a greater number of moles. Now when I come over here, it says they have equal masses. It says they have equal masses. Now I need you to understand that equal masses does not mean equal number of moles. So because you have equal masses, it does not mean you have equal number of moles because O2 and N2 have different molecular weights. Equal masses does not mean equal moles. So the one with a higher number of moles is going to have a higher pressure. Which one would have a higher number of moles? Now, if you can do this in your head, and I cannot do this in my head, always make up numbers for yourself and convince yourself with numbers which one would have a higher number of moles. For example, I know they have equal masses, right? So I'm going to make up numbers. I want to say I have 2 grams of O2 and 2 grams of N2. I can do that. I can make up numbers. It doesn't matter any number as long as I have the same number, the same mass. You can do 10 grams and 10 grams, 20 and 20. Okay, so now 1 moles of O2 is 32 grams, so the grams cancel out. I get 0.0625. Now, 1 mole of N2 is 28 grams, so the one you end up having is 0.0714 moles. Alright, so if they have the same masses, which one is going to have the higher number of moles? N2 is going to have a higher number of moles because it has a lower molecular weight. So if you have the same masses, the one with a lower molecular weight is going to have higher number of moles. Okay, and I just convince you with numerically that is true. So N2 has a higher number of moles, which means N2 is going to have a higher pressure. So the answer would be N2. Yeah? Okay, remember this. Every time you're not sure about things, just make up numbers for yourself and then convince yourself with values, with numbers, which one is the correct answer. Alright, next one. Which gas has a greater average kinetic energy? Hopefully, what you are telling me right now, even though I can't hear you, is that this is the easy one. Which one has a greater average kinetic energy? We said that average kinetic energy is dependent on temperature, is T dependent. Average kinetic energy only depends on temperature. Now, do you agree that they are in the same flask? If they are in the same flask, that means they have the same temperature, so they have the same average kinetic energy. Yeah? Okay, beautiful. Next one. Which gas has a greater velocity? So average kinetic energy, that depended on temperature. Velocity. What does velocity depend on? We talked about that last time. Remember, the velocity, the speed, how fast you're running around, it depends on molecular weight. It depends on the molecular weight. The lighter atom can move faster. Which one is lighter? We said N2 has a molecular weight of 28. O2 has a molecular weight of 32. Which one is lighter? N2. The lighter you are, the faster you can move around. So far, so good? Okay. I like this kind of problems. So make sure you go over this and you get this down. Let's continue with gases. We have one more thing to talk about for gases. The last part of gases we want to talk about is density. We're going to talk about density of gases. Now tell me, let's go back to weeks ago. What was the formula for density? Let's go back to the basics. Density is mass over volume. I can almost hear you saying that. Good. So density is mass over volume. Perfect. And every time we talk about gases, ideal gas law is PV/RT. Yeah? Okay. Now, we said that density is mass over volume, right? And gases, any kind of gases, we have PV/RT. That's the ideal gas law. What I'm going to do, instead of moles, I'm going to write moles as mass divided by molecular weight. I can do that, right? I can do that because how do you figure out moles? To figure out moles, you would take the mass and you divide it by the molecular weight to figure out moles. Do you agree? Oh, I forgot the RT. Because look over here. Here you had mass, you divide by the molecular weight, you got moles, right? So mass divided by molecular weight, you get moles. So instead of writing N, which is moles, I'm going to write down mass over molecular weight. Can I do that? Sure. Because mass divided by the molecular weight would equal number of moles. Beautiful. Now, if you look at this, you're probably going to see where I'm going with this. If you look at this, you're going to see that what we have now, we have volume in this equation and we have mass. So now we have volume and we have mass. And density is mass over volume. So what I'm going to do, I'm going to rearrange this. I'm going to rearrange this. So I would end up having the mass and volume on one side. Mass over volume on one side. Because mass over volume would equal density. That would be equal P times molecular weight over RT. So all I did, I had moles. I said to figure out moles, I have to divide mass by molecular weight. So I can just write mass divided by molecular weight is moles. Okay. So now I have volume and mass. These are the two components I need for density. And what I need to do, I need to have mass over volume. So I'm going to rearrange. I want to move things around that I would have mass over volume on one side. If you do that, then it's going to be mass over volume equals P times molecular weight over RT, and this is our density. So far so good? Okay. So, density of gases. And the symbol for density is rho. It likes that. Okay. That's its symbol for density. It would be P times molecular weight over RT. Yeah? Okay. Now, I'm also going to rearrange and find a different form of this equation. A different form of this equation, and I want to rearrange to isolate molecular weight. Molecular weight would equal density times RT over P. Again, these are all the same. These both all goes back to this. I'm just rearranging to isolate what I want, to solve for what I want. So far, so good? Okay. Now, these are two equations that I want you to know. Again, you can always, as long as you know this one, you can always rearrange on exam and get these two equations. But on exam, you have way too much going on. Way. It's good to know the equation, to have the formulas in front of you so you can just plug it in. Now, one thing I want you to pay attention to is mass and molecular weight. If the molecular weight goes up, what happened to the density? The density is going to go up, right? If you have a higher molecular weight, you have a heavier atom, the density is going to go up. Yeah? Okay. Beautiful. So far, so good. Now, let's do a practice problem. Here's our problem. I'm giving you the percentage of, I have a gas, it's 74.7% Cl, the rest is carbon. I give you the density, you have the temperature, you have the pressure. I ask you, what is the molecular formula? So you have to kind of remember previous chapters to do this problem. Molecular formula. Do you remember? I know it's been a while. Do you remember percent composition problems? Yeah? Percent composition problems? Yeah? Okay, so go back to that. Definitely review that. So if you remember, percent composition problem was that if you have a elemental composition, if you have a percent elemental composition, which I have right here, I have a gas, it has some formula, I don't know what the formula is, it's 74.7% Cl, and the rest is carbon. So I have the percent elemental composition, I can figure out the molecular formula. I can figure out how many Cl and how many carbon. And the way to do this, I always like to give people rules. You would go percentage to gram. You would convert gram to moles using molecular weight. And then you would divide by the smallest number of moles. And you would divide by, let me write it nicer, by the smallest number of moles. And then when you did that, what you would end up getting is a ratio, right? You would end up getting a ratio, and a ratio would give you the empirical formula. And from there, you could figure out the molecular formula. Okay, so I know it's been a while since you've seen a percent composition, so let's go over it one more time to make sure you remember it. So percent elemental composition is when you don't know the formula, but you know the percentage of each atom. You have 75.7% Cl, the rest is carbon. So now I want to figure out the molecular formula. And these were the rules. The first thing, you do percentage converted to gram. Second, gram converted to moles using molecular weight. Then you divide by the smallest number of moles to get a ratio, and the ratio would be empirical formula. And to remind you, what's the empirical formula? Empirical formula is the simplest whole number ratio. Simplest whole number ratio. Basically, the simplified version of the formula is a simplified version of the formula. Is the simplest, lowest whole number ratio. And then once you figure out the empirical formula, then you could figure out the molecular formula from there. Yeah? Okay, so hopefully now you remember this. Now let's do this together. So, the first thing you need to do is percentage to gram. And because everything adds up to 100%, I can take the percentage and I can say that's my gram, because it's a percentage is a ratio, and they would have to end up being 100%, right? It would have to end up being 100%. So if I have 74.7%, what I can say, I have 74.7 grams of Cl. Okay, now the rest is carbon. Again, we said it has to end up to 100, so it would be 100 minus 74.7 grams. That would tell me the grams of carbon. So percentage to gram, that was our step 1. Then what I'm going to do, I want to convert grams to moles. 1 mole of Cl is 35.5 grams. So what I get is 2.11 moles of Cl. Now I'm going to convert grams of carbon to moles. 1 mole of carbon is 12 grams, so grams cancel out. I get 2.11 moles of carbon. So far so good? Okay, so I took the percentages and I can just convert it to gram. I say the percentages are the gram because they have to end up to 100 anyway, so I could do that. Now, because I have to end up to 100, if Cl is 74.7 grams, if I subtract it from 100, that would give me the grams of carbon. Then what I did, I converted grams to moles using molecular weight. Okay, what is the next step? Divide by the smallest number of moles. Divide by the smallest number of moles. Okay, what is the smallest number of moles? 2.11, right? They both have the same. 2.11 is the smallest number of moles. So I'm going to divide them by 2.11. If I do that, I get 1 and I get 1. So that is the ratio. That is the ratio that I get. That is the ratio that I get. Okay? So now, what does that mean? That means I have 1 carbon and I have 1 Cl. I have 1 carbon and I have 1 Cl. Now, what is this? This is the empirical formula. This is the empirical formula. It's a simplified formula. Okay? So far, so good. So hopefully you remember percent composition now. Now, if you remember, if you have empirical formula, but from the empirical formula, you need to figure out the molecular formula. To be able to do that, to be able to go from empirical formula to molecular formula, what you need, do you remember? Tell me, what do you need? What you need the molecular weight. You need the molecular weight. So I'm going to take a step back. I'm going to slow right now to just make sure that everyone remembers the percent elemental composition. So we had the percentage of the element. We convert percentage to gram, divided by molecular weight, we got moles. We divided by the smallest number of moles, we got a ratio. This ratio was the simplest whole number ratio. This ratio is our empirical formula. We have one more step to go. We have to convert the empirical formula into molecular formula. To do that, what we need molecular weight. So what I need to figure out, I need to figure out the molecular weight. Can I figure out the molecular weight here? Yes, I can. Yes, I can, because you know the formula for the molecular weight of gases. Molecular weight equals density times RT divided by pressure. And I have all the variables to plug in to be able to figure this out. Okay, look at this problem. Do I have the density? The density is given to me. I have a density, I have the temperature, and I have the pressure. I just have to make sure they're all in the right unit. So density is 9.08 grams per liter. Now R is my constant, 0.08206. The unit for that constant is ATM times liter over moles times Kelvin. Okay. Now the temperature is 100, but I have to add 273 to it to convert it to Kelvin. So far, so good. Now pressure is 750 millimeters of mercury. What do I need to do? I need to convert it to ATM. 1 ATM is 760 millimeters of mercury. Okay. All right. Perfect. So I had everything that I needed, and I were able to convert it to the right units. So when I plug everything in, what I end up getting is 282 grams per mole. 282 grams per mole. Okay. Now let's see if you remember. So if you come over here, this was our empirical formula. Our empirical formula was C1Cl1. Okay? And we want to figure out what is our molecular formula. Now, we know our molecular formula has a molecular weight of 282 grams per mole. Now, can you calculate for me really quickly right now? Can you calculate the molecular weight of C1Cl1? Okay, calculate the molecular weight of C1Cl1. One carbon, molecular weight of 12 plus Cl, molecular weight of 35.5. So if you add them together, what you end up getting is 47.5 grams per mole. Okay. So my simplified equation has a molecular weight of 47.5, but my actual equation, my actual formula has a molecular weight of 282. How do I get from 47.5 to 282? Divide 282 by 47.5. When you do that, you will see that you would achieve that if you multiply it by 6. If you multiply it by 6, you would achieve that. So that means this is the actual molecular weight. This is a simplified molecular weight. To get from the simplified to the actual, I had to multiply everything by 6. So what is my molecular formula? It would be C6Cl6. That would be my molecular formula. This was a good problem. We did gases, and we did a little reminder of what is molecular formula percent composition. That is my molecular formula. Yeah? Okay, perfect. I did say this is the last thing, and I lied a little bit. There's one thing I could do that. There's one thing I want to mention very quickly. I'm not going to spend too much time on this, but I just want to mention it so when you read or hear about this, you know what I'm talking about. Dalton's law of partial pressure. You hear that word all the time, partial pressure, and it's nothing fancy. I'm not going to spend too much time on it at all. But I want you to just kind of understand what do they mean when they say partial pressure. So right now, in the room that you're in the air, you have different gases, right? You have H2 gas, you have O2 gas, you have N2 gas, right? So you have different gases, and they all would add up to the total number of pressure. And each gas is going to have a pressure, right? Each gas is going to have a pressure. And when you add them up, it's going to add up to the total pressure. So because you have several gases in there, what they say this is a partial pressure of N2. What do they call it partial pressure? Because if you look at the total number of gases, there is this, but there is other pressure of the gases that would add up to that. So when they say, okay, find out the partial pressure of N2. It's nothing fancy. You still use the same equation you've been using. What it just means is that it's partial pressure because you have other gases in there too. That's what they call it, partial pressure. If in a room there was nothing but N2, they would say find the pressure of N2. But if they say find the partial pressure of N2, that means beside N2 there are other gases in the room. It doesn't change how we solve it. We use the same equation, same exact thing, but it just say partial pressure because other gases are in the room too. Sounds good? Okay, beautiful. Next time we're just going to do a couple practice problems and we are done with gases. Nice.